Okay, now in many cases, you're going to find out that the particular solution or the trial solutions that you find will have some problem, right? That is, the form of the forcing terms mimic the form of the homogeneous solutions that you get. And when that is the case, what you do is that you keep multiplying by t or x to avoid the linear dependency on the homogeneous solutions in the particular solutions. So this is part of the procedure that I showed earlier, that for you can choose a trial solutions and use the method of undetermined coefficients to find particular solutions. Now, some particular solution or the trial may duplicate in terms in homogeneous solutions, and when that is the case, you multiply it by t to the power k. So k can be 1, can be 2, can be 3, so on and so forth, to avoid forming linear dependency on homogeneous solutions. All right, so I'm going to show you this next example when we run into that very problem. So the right hand side, the forcing term is 12 times e to the 2t. Now I'm going to give the trial solutions. I'm going to run through the problem as we did in 2, 3, and 4 to see if there's any issues that we are dealing with. All right, so the trial solution is y sub p equal to a times e to the 2t, and y prime is equal to 2 times e to the 2t, and y's p double prime is equal to 4a times e to the 2t. Okay. Now you substitute all of these functions into the differential equations. So substitute y sub p, y sub b prime, and yp double prime into the differential equations. We get that y double prime, which is 4a times e to the 2t, minus 4 times 2a times e to the 2t, plus 4 times a times e to the 2t, now equal to 12 times e to the 2t. For e to the 2t is the common factor on both sides of the equation, so you can divide it both sides by e to the 2t, and you're left with 4a minus 8a plus 4a equal to 12. And if you notice now that on the left hand side you have 0, and this is equal to 12, right? So this is a false statement. So what's the problem here? The problem is that the right-hand side of the differential equations has the functions e to the 2t. And if you solve this differential equations, the homogeneous differential equation, you will see something. So if you consider the homogeneous equations, so this is of the form y double prime minus 4y prime equal to plus 4y equal to 0, then you turn this into a characteristic equations of the form r squared minus 4r plus 4 equal to 0. You have a repeated root of r equal to 2. So the solution is going to be, so the homogeneous solution is the linear combinations of the two solutions y1 and y2. Right? So for y1, so let me be careful here. So y1 in this case is going to be e to the 2t, and y2 is going to be t times e to the 2t. Or rather, if you go back to the lecture of reduction of order, you will see that k1 times t plus k2 altogether times e to the 2t. Okay, so the left-hand side, or the homogeneous equations, will give you e to the 2t for the first solution, and the second solution is a linear function multiplied with e to the 2t. Okay. Now, what about the right-hand side? The right-hand side mimic e to the 2t. Therefore, you cannot use this trial solutions of a times e to the 2t. You cannot even use t times e to the 2t for the trial solution, because it's also mimic the homogeneous solutions. The trial solutions in this case should go up to y sub p equal to a times t squared times e to the 2t. Okay, so the trial solution should be y sub p equal to a times t squared times e to the 2t. Again, the issues with this calculations where you have a false statement is that the forcing term, or the right-hand side, mimic the homogeneous solutions. That is matched with e to the 2t, and so to avoid that, we're going to multiply e to the 2t by t. However, you run into the same problem because the second solutions mimic t times e to the 2t. And therefore, you have to go up to t squared times e to the 2t, and that is the trial solutions that you have to use. Okay, so that is when the first guess failed. Right? So you move on to the second guess, and to the third guess, the fourth guess, so on and so forth, until you totally avoid the linear dependency on the homogeneous solutions. Now let's move on to a bigger problem here that, again, you're going to solve this differential equation using the trial solutions that you just make. Okay. So the trial solutions here is y sub p equal to a times t squared times e to the 2t. So y sub p equal to a times t squared times e to the 2t. And therefore y sub b prime is going to be a times 2t times e to the 2t plus a times t squared times 2 times e to the 2t. Or you can simplify this further. So you get e to the 2t as the common factor, or 2a times t plus t squared times e to the 2t. Now for y sub p double prime, so you got 2/8. You multiply with the derivative of t plus t squared, that is 1 plus 2t times e to the 2t, plus the first function multiply with the derivative of the second function. Then simplify this, simplify the expression in the bracket. So you get 2a times 1 plus 2t times 1 plus 2t plus 2 times t plus t squared, and you take e to the 2t as the common factor. You're left now with 1 plus 2t plus 2t plus 2t squared. E to the 2t, simplified further, you get 2a times 1 plus 4t plus 2t squared times e to the 2t. Then you're going to substitute the second derivative, the first derivative, and the zero derivative into the differential equations. So substitute y sub p prime, and y sub p double prime into the differential equations. We get that. So y double prime minus 4y prime, so y double prime is 2a times 1 plus 4t plus 2t squared times e to the 2t minus 4y prime. That is 4 times 2a times t plus t squared times e to the 2t plus 4y, which is 4 times a times t squared times e to the 2t equal to 12 times e to the 2t. But e to the 2t is the common factor on both sides of the equation, so you can divide both sides for that to get rid of e to the 2t and simplify the equations further. You're left with 2a times 1 plus 4t plus 2t squared minus 8a times t plus t squared plus 4at squared equal to 12. Okay. Now distribute 2a and negative 8a into the parentheses. You get 2a plus 8 times at plus 4a times t squared minus 8a times t minus 8a times t squared plus 4a times t squared equal to 12. Alright, so 8at minus 8 times at, so they cancel out. You have 4at squared minus 8at squared, so they cancel out. And you're left with just 2a equal to 12, or a is equal to 6. Therefore, the particular solution is y sub p equal to 6 times t squared times e to the 2t. and that is the particular solutions. You have the homogeneous solutions up here, right? From y1 and y2, you can form a homogeneous solutions of the form. So y sub h is equal to c1 times e to the 2t plus c2 times t times e to the 2t. Now, how could I get this? Now, I could recommend you to go back to lecture 10, when we talk about repeated root and reduction of order. First you get two solutions, then you can write the general solutions or the homogeneous solution. In this case, for the case of repeated root. Alright, so with homogeneous solutions and with the particular solutions that we just found, you can write down the general solutions. So the general solutions, is y equal to y sub h plus y sub p, for y sub h is equal to c1 times e to the 2t plus c2 times t times e to the 2t plus 6t squared times e to the 2t. And of course, the value of c1 and c2 can be found using the initial conditions. So in this case, you don't have the initial conditions. That is just the general solutions that we need to find.